All right, hello everyone. So this is going to be the pre-lab lecture for the lab where we're going to be measuring the specific heat of water. So I'm going to be briefly giving you the overview of the theory, and then I'm going to show you this, or introduce you to the pivot platform and give you kind of like let's say breakdown of the experiment, how to do the experiment on pivot, sort of like a step by step, let's say introduction to the tools that pivot allows you to use to measure things. And it's relatively straightforward. um, if you use it for a couple of weeks, I'm certain you guys will enjoy using pivot. It allows you to take measurements, uh, plot graphs and things like that. So um, that's why I'm using the pivot for the our online labs. All right, so let's start with our the specific lab, which is measuring specific heat of water. So for this experiment, we're going to be, as the title suggests, right, investigating how to measure the specific heat of water. Okay, now there are a couple of things important to understand for this experiment. First of all, what is heat? Okay, so generally heat, which we use Q for that. Um, Heat, in a way, you can think of like this: is a energy, but is a specific type of energy, or you can say it's a flow of energy or transfer of energy from one system to another. So, in a way, is you can say that it's a transfer or flow of energy um, from let's say generally environment or from your system or things like this. It's like this: to your system or out of your system, to or out of your system. All right, that means heat is amount of energy that is transferred to the system or out of the system by some kind of mechanism. And there are other mechanism to transfer energy, and hopefully you guys remember um, from the mechanics class that there's another transfer of transfer mechanism of energy, and that was the work done. So work done, right, which we use W for that, was also transfer of energy mechanism. And the equation for this was integral of F dot dx, or like let's say dr, right? And going from basically R1 to R2. That was general equation for the work done. And it allowed you to transfer mechanical energy into your system and allow you that energy to be converted into kinetic energy or potential energy and things like that. Now, for the heat, then, it is a transfer of energy through a different mechanism. This is always only happen when the system that you have has a different temperature compared to, let's say, environment. So generally, this transfer of energy because of the difference in temperature, where work here is due to some kind of force, changing the position of the object and things like that. So we're gonna pretty much looking at the heat as a transfer mechanism for us. That means it's a transfer of energy because of the change in temperature. But it's still transfer of energy, which has units of joules, and energy again can do other things, right? So energy can be converted to kinetic energy, potential energy, and things like that. Well, in this particular, let's say, experiment, and whenever you talk about thermodynamics, we assume that when you transfer energy, this energy goes specifically to change the temperature or specifically to change the phase. That means, in a way, those are the two things that we're going to be um, sort of like, let's say, getting a result because of the energy transfer. That means when you're transferring energy as heat, it can either increase temperature of your system, or if you are reaching one of those, let's say, critical points, right, boiling, freezing, and things like that, it can then also change phase. Now, for now, the equation for heat to change the temperature is an equation that is allows to see how the or amount of energy that goes into the system, right? Basically, what does it depend on? So that means what are the quantities that can change the amount of heat required to change the temperature of your system. So for example, Q, which is the energy, to change the temperature, proportional to the mass of your substance. That means more mass you have, more heat needed, right, to change the temperature. That it's proportional to the mass. But it's also proportional to the change in temperature by by how much you want to change your temperature. Do you want to change your temperature by 1 degree, or by 20 degrees or 30 degrees or 50 degrees, right? So that means this delta T, change in temperature, also affects how much energy required to transfer into your system. That means Q is directly proportional to those quantities: mass in kilogram, and then delta T can be in either degree Celsius or Kelvin. And the reason is degree Celsius or Kelvin because this is change in temperature. Whenever you're considering change in temperature, delta T in Celsius equals to delta T in Kelvin. Okay, that means they have equal steps, or like change in steps. So like let's say delta T in Celsius, if it's a 20 degrees change in temperature in Celsius, it's exactly also 20, uh, we usually don't say degree Kelvin, we just say 20 Kelvin change, for that scale as well. All right. So taking those two, let's say how the Q is related to those quantities. That means if you have, let's say, water in some kind of container, how much energy will go into changing the temperature of this water depends by, how much water you have, its mass. And also depends on, let's say you put a thermometer and measure, okay, let's measure initial temperature. Then it, let's say, depending on what is your final temperature that you want, right? Then, the amount of heat transferred to increase temperature from initial to final will be determined also by that, difference. Now, generally you can say it like this: if Q is proportional, then mass and delta T. Usually in physics, or in, let's say in physics, when we go from proportionality sign to equal sign, we introduce a constant. We call it proportionality constant. And in this particular, equation, that proportionality constant is what we call specific heat. So then Q is equals to, so M times delta T, then that proportionality constant, which in this case given with the lowercase c, and then this c here is the specific heat. So specific heat is pretty much, you can say it's a proportionality constant. And if I rearrange this equation, then C is equals to Q over M times delta T. So from here, even you can pretty much see the units for the specific heat. So Q here is joules, and at the bottom right is mass times delta T, which means it's kilogram, then degrees Celsius, let's say. So those are the units for the specific heat. So in a way, specific heat is a proportionality constant, but also very specific to a substance itself. So water has a different specific heat, because to increase the temperature of, let's say 1 kilogram water by 1 degree is different compared to if it's aluminum, compared to if it's even ice, compared to, let's say, it's mercury or whatever it is, right? So specific heat is very specific to the substance. So in this type of calculation, then again, you can see, right, heat has to be in joules, mass has to be in kilograms, and change in temperature has to be in Celsius. Then we can calculate and get the specific heat for a substance. So for example, specific heat of water, let's say the theoretical or accepted value is then equals to 4,186 joules per kilogram degree Celsius, or degree Kelvin. So this is technically going to be your, theoretical value. So 4,186 joules per kilogram Kelvin. That means if you have 1 kilogram of water and you want to increase its temperature by 1 degree Celsius, you need to transfer 4,186 joules into your system. Okay. So, and then you can change the temperature of 1 kilogram of water by 1 degree Celsius. All right. So generally, water has liquid water has one of the highest specific heats, and that's actually a very good thing, because this is in a way represents our the substance's ability to resist the change in temperature. So let's say when you transfer 4,186 joules, right, to 1 kilogram of water, you change it by 1 degree Celsius. If you transfer 4,186 joules into, for example, 1 kilogram of I don't know, methyl alcohol, you will increase by 2 degree Celsius and things like that. So the idea here is that higher the specific heat, harder it is to change the temperature of a substance. And it is good for water because, let's say for example, our oceans, right? So during the summer, they are absorbing a lot of heat from the sunlight, and during the night, like say during the day, right? And during the night, they are releasing most of that heat. Because remember, the heat is the energy that is transferred into system or out of the system. So during the day, water is, let's say, cooler than the air, the air right above it. So let's say the air is hotter than water, and the heat, which is the transfer of flow of energy, always goes from hot to cold. So this is always, a one-way direction for the heat. It always goes from hot to cold. Okay. So that means, naturally, right, that's the direction of the heat. That means when air is hot, water is, let's say, cooler, right? Then heat goes from air to water, and water warms up. But it doesn't warm up, excuse me, it doesn't really warm up too much, right? Maybe during the day, like few degrees. If the water had low specific heat, then all that energy absorbed would have basically maybe boiling the water, right, in the oceans. And that's not what you want, right? You don't want, like, let's say, during the day of boiling, oceans. And during the night, when after sunset, the air molecules, right, basically the air, right, the environment starts cooling down. So then the water actually is the warmer or hotter object. So then it starts losing heat to air, to environment. So imagine now, if the water loses heat, well, if it loses heat, its temperature decreases. When its temperature decreases, then because it has a higher specific heat, its temperature decreases just a few degrees, which is good. Otherwise, let's say if it loses all that energy to environment, right, to air, maybe it would go all the way to, let's say, freezing. And you don't want that, right? You don't want boiling oceans during the day and freezing ocean during the night because of that thermodynamics processes. So anyways, the water has a large specific heat, and this is the accepted volume. And now we are going to then do experiments verifying this. Okay, we're going to be verifying the specific heat. Now, there's a reason that I put those two together initially, because again, heat and work are two ways of transferring energy. That means, if you remember, the in a mechanics class, you also learn about the rate at which you transfer energy. So the rate at which you transfer energy, which is basically the W dt, this was defined as the power, right? So this was the power. That means, in a way, you can write as transfer of energy per unit time, right? So let's say, the rate at which you transfer energy. Well, now if the transfer of energy is heat rather than work, you can still, in a way, write it like this. It's dq dt. Basically, uh, how fast do you transfer, heat into the system? So that means that's basically the power. So in this case, then one of the things I can do here is I can rewrite this q, which, in a way, you can say that, like, let's say then dq is equals to power, let's say dt. Okay. So, and if the conditions are right, more of like a, let's say, constant rate and thing like that, you can pretty much say q is then equals to p times delta t. Okay. So because if I take the integral of both sides, and the rate is constant, P will come out. So then you have Q on the left side, and this will be P integral of dt, which just gives you P times delta T. That means this is then the equation that can be used to find heat if you have, let's say, way of calculating the transfer of energy, the rate. So let's say if you are given power, and then let's say power, remember, is amount of energy per unit time. For example, if you have a light bulb and the light bulb says 60 watts, that's basically the power of the light bulb. 60 watt is just basically 60 joules each second. That means the transfer, of energy is 60 joules each second. So let's say light bulb loses that much energy each second. So that means if you have the rate, that means the wattage of your source, and then you can measure how long, you are using that, right? How long you're transferring in or out of the system, then you can calculate the heat. And that's basically what actually we're going to do in our experiment. Okay, so hopefully you guys were able to follow this lecture. Again, remember, so the pre-recorded allows you to go back and watch it again. Now I'm going to go back or go to the Pivot Interactive and gives you introduction, and we're going to basically use it most of the things that we just talked about here. All right, so here's then the experiment that we have on Pivot Interactives. If you haven't, make sure that you guys go and register for Pivot Interactive, so then you have access to the experiment. Now you can see, right, so the title says measuring the specific heat of water, and in this activity we'll explore the different lab setups used to find the specific heat of water. Okay, and I think I already gave you equation, right? And in terms of how to find specific heat, using the equation, right? It's, heat equals mass times, specific heat times change in temperature. Then you can rearrange that to find specific heat. Now, one of the things we're going to do here's in first experiment. So the Pivot Interactives generally has a video of an experiment, like over here, right? Video of an experiment. And your goal will be to watch the experiment, be able to then make measurements of some of the things, and then use that to calculate some kind of result. So let's see over here. So our goal is to determine how much energy is required to increase the temperature of 1 gram of water by 1 degree Celsius. The video below shows a beaker of water heated by 25-watt light bulb. That means that's basically the power, right, of that light bulb, and that's going to be the source of our energy, right? Basically, the light bulb um, is the source of energy, and it's transfers 25, remember watt means joules per second, right? So transfer 25 joules per second into our system, right? The display shows the temperature of water, and you can also click the tools button, which is right here. If you click this, you can see, right, you can get a timer right here. So to show a stopwatch for measuring time. All right, so let me put this here. The experiment itself is relatively straightforward. As I said, right, you have beaker with water, and then it is hooked up to the let's say to the computer, which gives you the change in temperature. There is also a way for us to find the mass of the water. Remember, the equation for the specific heat was Q over mass times delta T. And I also said that Q, you can get it from the power times delta T, right? So basically those are the sum of the equations that you're going to be, using. That means, in order for you to calculate C, look at that equation, those equations, and, try to figure out which quantities, right? Which quantities, which, let's say measurement do you need in order to get the specific heat. All right, so here's an experiment. All right, so that was the experiment. That means going Going back, you can see, right? So here they take the beaker, put it on a scale, and that's the mass of the beaker itself. And then they pour water in it. And that's the mass of beaker plus water. Should allow you to find then the mass of the water. Afterwards, they start heating up. You can see, right? So the light bulb is on, and in a way, that's the instant where you start, you know, uh, taking measurements. That means you can go back here. So this is the instant when they turn on the light bulb. Okay, so find that instant. Let's say there you go. And then from here, you reset your timer. That means temperature that you see is your initial temperature. And then you can then from here measure the time. And if you reset the timer, it's basically going to start from here. And then you can just use this to measure how long it will take. And in terms of like a the temperature is different, right? That means you get your delta T for this particular, change in temperature. Okay. So it allows you to basically make a measurement. And once you're done with the measurement, then you can, calculate. So let's say, for example, right, I think it was 22 degrees Celsius. And then you measure, okay, so all the way to 28.3 degrees Celsius. And then you look at your time, right? So 28.8 minutes, convert to seconds and everything, like let's say 25 watt as a 25 joules per second, calculate the heat, measure the mass, calculate the change in temperature, and calculate the specific heat using those equations. All right. So relatively, straightforward. You're going to use those, let's say information, right? Those measurements to calculate the specific heat. Now, one of the things I want you guys to do is you technically have an option to type it out here in your answers, your calculations, but it's not easy to do all those calculations here. I, highly recommend you guys um, do all your work on a clean sheet of paper, and then take a picture of your work and then transfer it here. They have this option that you can upload a picture here, so you can basically mix your answer in terms of some things that you type, like an explanation, and then all your work as a JPEG file, right? So take a picture and upload it here. It's easier for you, it's easier for me also to be able to follow. All right, so then you're going to be able to use that to answer some questions. Okay, so those are basically the questions based on the theory, based on the experiment. And I don't want to kind of go over that because it's basically I want to see you being able to figure out the answers for those. um, what I'm going to talk about again here is experiment 2, which is testing your hypothesis. So in this experiment, one of the things here you're going to see is that when you do that first experiment, you're going to see that your volume might be slightly off. Okay, that's because there are a lot of let's say variables into play, because one of the things we have here is that specific heat, when they're measured 4,186 joules per per kilogram degree Celsius, that's done in experiment that has been very accurately measured. Our experiment wasn't. So one of the things we can do here is you can see that there are some let's say theories or hypotheses, right, to change the setup of our experiment so that our experiment is more reliable, more accurate. And there are several experiments, so basically insulated from environment and things like that, because glass, it's still, right? If you, let's say, imagine if you have that glass beaker, if you pour hot water and you touch the beaker, the beaker itself is going to be very hot as well. That's because, it allows some of the heat to escape through the glass, right? So if you insulate it, maybe it will prevent the heat from leaking out. And what we're going to do here is you're going to do this experiment where now you have a foil around the glass beaker, and then you're going to repeat this experiment. Once you repeat this experiment, you're going to describe, your results. So it says describe your process and results, which experiment gives best, result, and so on and so forth. So again, some things that you can answer after your experiment is done. But again, pretty much same idea. See, you are repeating the experiment, but now you have basically foil, right? Aluminum foil, which is acts like a, so like a, in this particular case, conductor. All right, so you read that, let's say, the hypothesis and then test it. After that, you have another experiment where now we're doing something different. So let's say if you have aluminum foil, what do you get? And what if we have something different? Like, let's say, instead of conducting material, we have a insulating material, like a styrofoam cup or double walled coffee cup, or Dewar, which is basically an equipment that was done by John Dewar to help the you can say pioneering efforts to create liquid oxygen. So one of the things we're going to be able to do here is we're going to test different basically experimental setups while repeating the same experiment. So to change the type of experiment, we're going to click here, change. Then you can see, right, you're going to do trial one, styrofoam cup, then trial two, is right, double walled coffee cup, and then the Dewar, like that. So then repeat the experiment and then show all your work here. Again, do your work on a piece of paper, like let's say, and use your result to come up with a conclusion, right? Which apparatus works best, and support your claim with evidence. By evidence, we mean like your experimental data, calculation for specific heat, and let's say percent difference and things like that. Okay, so you should be able to then look at all those experiments. So for example, again, right? So you're not doing anything different compared to the first experiment. You just have a different apparatus, okay, which allows you to, you know, um, much better isolate your system from environment, and all the energy that is given off by the light bulb is then directly goes into changing the temperature of water, compared to, let's say, uh, being able to escape into environment and things like that. All right, guys, so this is pretty much the experiment. If you have any questions, put it in a discussion board, or let me know through email.